Last time we talked about differential equations. Today I want to talk about initial value problems. Again, this is a little bit different from the textbook for the moment. We're just trying to introduce the subject. But we said last time that a differential equation tends to have an infinite number of solutions because when you integrate, you get that arbitrary integration concept that gives you a whole family of functions. One function for each integration constant, typically. So now what happens is, in a lot of models, we actually want a unique solution of the model, right? It has to satisfy a differential equation, and it has all these solutions. How do we pick out which one is our model solution? Well, we apply an additional thing called an initial condition, or initial conditions. And we'll say this: for an nth order initial value problem, that consists of an nth order differential equation, meaning the highest derivative is the nth derivative, together with n initial conditions, where you specify that y, the solution function at t0, is some number y0. This dot means derivative with respect to t, so y dot or y prime at t0 is some number y0 dot. So these are numbers on the right, despite the dot. This means it's the number that's the derivative at t0. And the n minus first derivative at t0 is equal to the function n minus first derivative at t0. So what happens in practice is you have an nth order differential equation. You apply n initial conditions. Initial, thinking of if t0 equals 0, then it would be initially. But at whatever initial point you have, t0, y and its first n minus 1 derivatives are specified. That's n initial conditions to go with your nth order differential equation. And in many common situations, this identifies a unique solution out of the n integration constants that come from integrating an nth order differential equation n times to try and solve it. So you find the solution set, then you apply the n initial value problems, and you can get a unique solution, hopefully. That happens in a lot of cases. So, here's just an example. Suppose the right side was only a function of t like we had last time, right? We said in that case you can just integrate both sides a la calculus and get the solution is y on the left equals the integral of f on the right. And if you apply the fundamental theorem of calculus, you can in particular then say the unique one that has its value at t0 equal to y0. Well, here's one antiderivative, is the integral from t0 to t, right? Fundamental theorem of calculus, one part of it. This is an antiderivative of f of tau, f of t, whose value at t0 is 0, because if you go from t0 to t0, then you get 0. So this is an antiderivative, the one whose value at t0 is 0. So if you just add y0 if you add c to this and put c equals y0, you get the unique solution that satisfies the differential equation and whose value at t0 is y0. So this is the unique solution that comes out of a first order differential equation when the right side is a function of t only and it's integrable, say it's continuous or something. So here's an example. Suppose I wanted to solve dy dt equals tangent of t together with an initial condition y of pi equals 1. We call this a first order initial value problem, a differential equation with one initial condition. For second order equation, we would normally want 2, and so on. What's the unique solution that satisfies the differential equation with the initial value? So we do this, we integrate both sides, integral of tangent t. How do we get that? All right. Well, we write tangent as sine over cosine. Remember this trick from calculus? You can let u equal cosine, the substitution. By the way, you're going to be good at integrals by the end of this semester. You let u equal cosine tau be a substitution. By the way, I only write this as function of tau because it's a mathematical faux pas to use the same variable t for the integral that you're going to evaluate it at. So if you're going up to t, then you just integrate tangent tau d tau instead of tangent t dt. You get the same result, but because tau or t is a dummy variable that falls out when you integrate and evaluate at the endpoints, it goes away. So we use tau or t or whatever letter we want, but in calculus we usually like to use a different letter than we use at the endpoints. All right, so integrate tangent, plug in t and pi and take the difference, right? But we let u equal cosine t, then du is the derivative of cosine t dt is minus sine t dt. And so let's see. So then cosine tau becomes u, sine t dt becomes minus du, and the endpoints have to be replaced also, right? This pi gets replaced with cosine pi as minus 1, t gets replaced with cosine t. So that's the u substitution theorem from calculus. Replace this with u, this with minus du, this with cosine pi, this with cosine t. And then the plus 1 hangs on the end. That's our theorem there, that you can solve this by integral f of tau d tau plus the initial condition. So the initial condition was y of pi equals 1, so we put 1 on the end. And here is the unique solution to this initial value problem. Well, integral 1 over u is natural log absolute value of u, and then we're going to plug in the two endpoints and take the difference. And so what we get then, we get minus ln of absolute value of cosine t plus ln of 1 plus 1, right, absolute value minus 1 being 1. Ln of 1 is 0, however, so, minus ln of cosine t, remember your properties of logarithms, it's the same as ln of cosine t to the minus 1, or 1 over cosine t is secant t. This becomes natural log absolute value of secant t plus 1. There's how you solve that problem. This is the unique solution. How can you check it? Big advantage in this course is when you have a solution to the differential equation, you can check it by plugging in. That's what we mentioned last time. So you plug in natural log absolute value of secant t plus 1 into here for y, and you find that on the left you'll find that you get tangent t matching the right. You can plug it in and check it. You can do that in your calculator sometimes too, depending on your calculator. So this is the unique solution to the differential equation that also has y of pi equal 1. Here are some plots of the curves. They look like this for various values of c. So if you just took solutions dy dt equals tangent t and put c arbitrary, you get all these curves, but the only one that goes through the point t equals pi, y equals 1 is this one. So these are all the solutions to differential equations between minus pi or between pi over 2 and 3 pi over 2. There's others out here. But there's only one that also satisfies the initial condition. That's the idea. All right. How about a unique solution of a second order initial value problem? With a second order differential equation, I'll specify y and y prime both at the same value of t, and we have a theorem coming up that says that will grant you a unique solution for a nice function here. And let's try it out. It turns out, we won't solve these for a while, but the set of all solutions is a constant times e to the minus 2t plus another constant times e to the 2t. You can check that these are solutions, and then there's two arbitrary constants suggest that it's all solutions. We haven't proved it yet. But we plug in both initial conditions. We plug in y of 0 equals 3 into this proposed solution. So we put 3 equals c1 e to the 0 plus c2 e to the 0. Here it is. And that gives c1 plus c2 equals 3. One equation for c1 and c2. Then we plug in y prime. We take the derivative of this and plug in t equals 0, and we get for the initial condition, we plug in t equals 0 to the derivative, we get negative 2 for y equals, and you plug in 0 for t, and it's minus 2 times e to the 0 plus 2 times e to the 0. This is the derivative of the function. And that tells us, by plugging in the second initial condition, that minus 2c1 plus 2c2 equals negative 2. Now you have two linear equations and two unknowns, c1 and c2. If you took linear algebra, you know that'll either have no solution, exactly one solution, or an infinite number. In this case of differential equations, with this nice function, it turns out that it's always the case where you get exactly one solution. So So we'll get exactly one solution to this, two equations and two unknowns. Here's the two equations and two unknowns. It turns out C1 equals 1, C2 equals 2. How do you solve that? Well, one way to solve these is to add a multiple one equation to another. If I take twice the first equation, add the second equation, 2C1 and the minus 2C1 will cancel, right? 2 times this one added to this one cancels. 2 times this one added to this one gets 4C2. 2 times this one added to this one is 6 minus 2 is 4. I get 4C2 equals 4 by adding, and then that tells me that C2 equals 1. Then I plug it into either equation, and that tells me, like plug it in here, that tells me C1 has to be 2. I'm sorry, what did I do here? Two times this one to this one gives me 4C2 equals 4. C2 equals 4, that equals 1 should be. And C2 then, C1 is 2. So I think oh, that's right, okay, this one. I just wrote this one. C2 is 1, and C1 is, C2 is 1, C1 equals 2. That should be a 1. All right. And you get 2 e to the minus 2t plus e to the 2t is the unique solution that satisfies the initial values and the differential equation. Well, here's an interesting one. The differential equation that comes up in your physics class, right? Force equals mass times acceleration. Well, force is mass times second derivative of position with respect to time. Suppose I have a rock falling over a planet. Here's y as the vertical direction. And we know that force from Newton's law is minus mass times a constant, g, which is 9.8 meters per second squared, or 32 feet per second squared, is just a constant. So the force is this constant minus the mass times the gravitational acceleration. And for the falling rock, ignoring air resistance. And force is also mass times acceleration, gives us this force equation. Mass times acceleration equals the known force of gravity from experiments. And so we have this equation. You can cancel ends on both sides and just get second derivative of y is minus g, a constant, where g is minus 9.8 or minus 32. G is plus 9.8 or plus 32, so the gravity is negative, pushes y negative. All right, and then we can apply initial conditions. Let's leave them arbitrary. At time 0, you have some initial height, y0. At time 0, you have some initial velocity, v0, which is the derivative of y. And so here's this interesting experiment Galileo performed to show that that really seems to be true for heavy objects that aren't too affected by air resistance, just by gravity. They found that heavy objects and much lighter objects, still heavy enough the atmosphere doesn't affect them too much, fell right together at the same rate. They took the same time to strike the ground. One of his students wrote that afterwards. I think that's true, that he did that. Well, how do we solve this equation? We can make a substitution. We can substitute v equals the derivative of y, and then the derivative of v is the second derivative of y. To rewrite the differential equation as dv dt equals minus g, a first order equation, by a substitution. Then we can integrate that, right? Integrate both sides. This side doesn't depend on t, so we integrate both sides and get v on the left and minus gt plus a constant on the right, where g is the acceleration of gravity. Now you apply one initial condition, y prime of 0 equals the number v0, and we put that in, and we get that, oh, if we put in t equals 0 and have v0 here, c1 must be v0. So this is, now we know v equals minus gt plus v0, where v0 is the initial velocity, g is the gravitational constant. And now v, however, is dy dt, where y is position. So this is dy dt equals minus gt plus v0, just putting back v equals dy dt from the substitution. Now we have a first order equation to solve for position. We can integrate both sides because this side depends only on t. Look what we get. Y equals minus a half gt squared, integrating that term, plus v0 t here, plus an arbitrary integration constant, c0. Now we apply the initial position. Y of 0 equals some number y0. Well, we put y0 here and 0 for t. We get c0 equals y0. And so now we have the unique solution of the initial value problem here. Y equals minus a half gt squared plus v0t plus y0 is a unique solution to the second order differential equation with two initial conditions. There it is. This is a very famous equation. You find it in your calculus book. You've actually seen it before if you think about it. And so we can solve a problem like this. Suppose we fire an object straight up. So it starts with an initial position. Maybe I'm firing it from a cliff 128 feet high. And I fire it upward with a 112 feet per second velocity. Ignore air friction. Find its height as a function of time. And find its peak height and so forth. Well, here's the model. D squared y dt squared is minus 32. I'll put in what g is this time. Y of 0 equals 128. Y prime of 0 equals 112. Right? Is the velocity. Positive 112 because it's upward. If I fire it downward, I have to use negative. Alright, so there's my initial value problem. The same one we just did. We could just plug in the numbers right away. Yeah, but if you integrate this twice, you'll get this equation here. And now I plug in these numbers. 128 for y0, 112 for v0, and 32 for g. And that integration tells me that the position of this cannonball, or whatever it is, minus a half 32t squared plus 112t plus 128 until it strikes the ground when this model is no good. So there's the result. Now how do you find from the solution of this model what is the impact time? Well, it impacts when y equals 0 is the assumption up in the picture. Right? Y equals 0 is the ground. I guess I didn't mark it clearly there, but y equals 0 is the ground. Then I simply put in 0 for y and I can solve for t. So you put in 0 for y and you get a quadratic equation. 0 equals this. You work that through and get actually that t equals 8 or minus 1. Minus 1 is if you ran the cannonball backwards in time to intersect the ground, assuming the model worked for negative times. What you have here is a parabolic trajectory and it intersects at a negative time with the Earth also. You want the positive solution, you put t equals 8. That's the impact time. How do you find its maximum height? You can set the derivative of this equal to 0. Remember we had the derivative up here, actually velocity, but you set the derivative of this function, so I'm moving it around too much. Take the derivative and set it equal to 0, and you get, let's see, minus 32, yeah, minus 32t plus 112 equals, is the derivative. Set that equal to 0, and you find out the derivative is 0 at 3.5 seconds. Plug in 3.5 into the solution, and you get the height at when the derivative is 0, but the derivative is the upward velocity, so that's the height when it instantaneously stops at its peak. And there's your solution to your physics problem, if you like. At 8 seconds, plug in 3.5 seconds to the height function and find out that you're actually 324 feet high. All right, well, let me mention one more thing here. If you, here's our first existence uniqueness theorem. This is in your book. It's 1.1 or 1.2. I forgot which one, or 1.3. This is a famous theorem, and it says that if you have a differential equation in normal form, we said this would be important. dy dt equals a function of just t and y. So first order equation in normal form looks like this. dy dt by itself on the left and a function of t and y on the right, together with an initial value like we just did. If you have those two things, differential equation in normal form of first order with one initial value, and suppose f is continuous and the partial of f, well, let's say first, if f is continuous in a rectangular region, a rectangle in the plane, t going between two numbers and y going between two numbers, that contains the initial condition, t0, y0, this has a solution, and it's unique on some interval, t0 minus h to t0 plus h for some positive h. And furthermore, if df dy partial to the right-hand side with respect to y is also theorem of piano for the first part, and the Picard-Lindelof theorem is the whole thing. Very famous theorem in differential equations for existence of uniqueness. Now we know why we need that initial condition. Here's the geometry of it. I made this picture in MATLAB actually. Here's all the solutions of differential equations. Here's the unique one that goes through the initial value t0, y0 for such an equation. This says that if you look at these curves, all these within the rectangle where f and df dy are continuous, have a single solution through them. So all the solutions go through without intersecting, and they fill the region because of existence, right? There exists a solution through every point, so there's a curve through every point, but it's unique, so they can't intersect. If they intersected, there will be two solutions for an initial condition. So this is the geometrical view of the Picard-Lindelof theorem, is that within a rectangle where f and df dy are continuous for this normal form, there are curves that flow through the region going through every point, and they don't intersect. So if I pick one initial condition, y of t0 equals y0, this point determines a unique curve through there as long as that curve stays in the rectangle. And so there's some interval minus h to plus h, or generally longer. It's not necessarily symmetric on both sides, but at least some interval, where it's unique. And actually it's unique where as long as it stays in the rectangle, because you say, well, it stops here. Well, you put your initial condition there, and there's a unique solution through there. You say, well, it stops here. Initial condition there shows that only one solution goes through there. So it stays unique as long as it remains within the rectangle. This is an important theorem for nonlinear differential equations. We're going to get an even better theorem for linear differential equations. Remember, we said that has a very important form called standard form also. So here's an interesting problem. Show that each member, these are the homework problems I'd like you to try for tonight. So that each member of the one parameter family of solutions, here's your solutions to this differential equation, a nonlinear equation because y is squared. Suppose that this has a unique solution together with when it's given together with y of 0 equals minus 1. How do I show that it has a unique local solution? Well, you can do something like this. You just look at the right-hand side for dy dt equals minus y squared. Here's your f of t and y. This one doesn't even have t up here. You can't just integrate both sides here because you try and integrate the right. Y is an unknown function. What's its integral? We don't know. Right? So we can't do the integration trick. There will be a trick coming up next time whereby we can do this one, however. But we call that f. Now this is a polynomial in y, so it's continuous, right? Then we look at partial of f with respect to y. That's minus 2y. This is a polynomial. It's continuous for all values of t and y. So we infer that actually f and df dy are continuous in the entire plane. Therefore, there's a unique solution through every point in the plane, and it remains solution as long remains unique as long as it remains anywhere in the plane. And so everywhere there's a unique solution through any initial condition. We know this thing is the unique solution as long as it remains in the plane. Well, doesn't that mean for all t? It actually doesn't. This has an asymptote at t equals minus 1, where it's not defined. And so this is unique wherever it's defined. The unique solution is good for t greater than negative c. Right? Assuming c is positive here. So y of 0 equals minus 1. You have to include the initial condition at t equals 0. And so if c is positive, as long as t is greater than negative c, this will be the unique solution. And you can do similarly on this one. Take f and df dy and say, well, suppose I knew this was the solution. What's an interval on which this is the solution? This is the unique solution. This one, I say unique solution of the differential equation continues together with an initial value. This has an infinite number of solutions. But if you also apply the initial condition y of 0 equals 1 to this, you'll find there's only one solution. Do this like you did on Monday. Integrate both sides. You can use partial fractions on this to integrate it. And you find the set of all solutions has one arbitrary constant because there's one integration. Apply this initial condition, you'll get the unique solution. So try that, and then you can try it also with this initial condition, y of minus 2 equals 2 ln pi, and you can find the unique solution of this one by integrating both sides. And then finally, try this problem here. One of Galileo's students said that Galileo dropped different balls from the Leaning Tower of Pisa. And how long did it take the balls to strike the ground? Use that equation we found and see if you can find out how long it takes. This one is just for fun. You don't have to do this last one. Let's leave it off. But this is a very fun thing. You should Google it and look for the video. I have it actually in the notes somewhere. Here it is. Here it is. Go to this website and look at it. It's fantastic. Alan Shepard, when he was on the moon back in around 1970, what is it? 71, brought a golf club up, snuck it up there, and hit a couple of golf balls on the moon, where there's no atmosphere, to see if he could really, and very little gravity. He makes it go a long ways, he hopes, and he said it goes for miles and miles and miles. It wasn't really that far because he didn't hit it that hard, but presumably somebody could hit it really long ways in the moon. You can figure out the equations. You don't have to do it for here, but I thought maybe you want to see the video to go with it.